Hello everyone, Mr. Hasty here again. We're going to start in section 12.3, which talks about solids and liquids. If you remember, 12.1 talks specifically about gases. So we're going to continue our discussion of the different states and matters. So we're going to talk today mostly about liquids, and then we'll do a separate video on solids. So if you remember, liquids have particular properties, namely, a liquid has a fixed volume but no fixed shape and is considered non-compressible. So what does that mean? If we have a liquid, and let's say we have 15 cubic centimeters of liquid, and it's in a cylindrical container, it'll take on the shape of a liquid cylinder that's smaller than the container. If we transfer it to a rectangular shaped container, it's going to take on that shape, but it's still going to be 15 cubic centimeters. And that's what we mean by having a fixed volume. Gases don't have that property. If we put gas into an object, it will expand to fit the size of this object. It also means we don't have a fixed shape. We can change the shape of a liquid by changing the shape of the container it's in. Now, what does it mean by non-compressible? Gases can be compressed. You can take something that's filled with a gas and shrink the size of it down and compress that gas. It's very, very, very difficult to compress a liquid. To compress a liquid, you have to apply such great amounts of pressure that it's somewhat extreme. And so we don't really consider a easily compressible substance. Now, oftentimes people will use the words liquid and fluid interchangeably, but it's important to understand that fluid just means a substance that can move around itself. So examples of fluids include both liquids and gases. They both have properties of diffusion. Just like if you put particles of gas into a different medium of gas, the particles will diffuse. If you put one liquid into another liquid, they will diffuse. And you can see that by putting food coloring in water. Now, at normal temperature and pressure, gases are always less dense than liquids. Gases are always less dense than liquids. That's why gas is always on top of the liquid and never the other way around. Now, you can have mixtures of gases and liquids under high pressure, like carbonated soda, but you have to have the right circumstances to make them even mix together, let alone to have a liquid be on top of a gas is kind of like this hypothetical situation that doesn't really occur in common everyday practice. All right. One of the concepts we talk about with liquids is we talk about their viscosity. So viscosity is a liquid's resistance to flow. So water, which is a liquid we think of a lot, is very non-viscous. It's very easy for water to flow. But honey or molasses or oil are more viscous liquids. They tend to have more resistance to flowing. And in fact, if you have honey, sometimes you can have a really hard time getting it out of the container because it takes such a long time to flow. Honey is considered a very viscous liquid. So what things contribute to viscosity? There's a number of things that increase the viscosity of the liquid. So we'll talk about what increases viscosity. To increase viscosity, the following things could be increased. These help to increase the viscosity. Number one, you could increase the attractive forces inside the material. If the attractive forces are higher, it slows the flow down, and thus you have a more viscous liquid. You could increase the particle size. larger particles flow more slowly. We talked about that when we talked about gases. So just as it's true for gases, it's also true for liquid. If we increase the size of the particle, it's going to flow more slowly. Now, one thing that's not really an increase, but the shape of molecules can affect the viscosity. If the molecules bind together a little bit better based on their geometry, they lock together a little bit better, it's harder for them to flow. This typically happens with very large molecules composed of a lot of different elements, like honey. Honey has a lot of chemical, like a lot of different elements wrapped up in there in these long chains of molecules, and that makes it so they kind of don't flow as easily. Simpler molecules tend to flow easier. And finally, if you increase temperature of the liquid, it increases viscosity. So an example of this is when you heat up things like molasses, they move slower. They tend to expand and they tend to move more slowly because they're more resistant to flow. So those things contribute to changes in viscosity, and they go the other way. If you were to lower those, it also lowers the viscosity. So all liquids have viscosity except for particular things that we call superfluids. They discovered superfluids by cooling helium down to negative 271 about degrees Celsius, and it had no viscosity. So superfluids are usually very cold liquids with no viscosity. Now, notice I said liquid helium. So they actually took something that's normally a gas and they cooled it down so much that it became a liquid, and that liquid had no viscosity because the particles were so small. Viscosity being one quality we talk about when we talk about liquids, another one is surface tension. So surface tension is the force exerted on the boundary of a liquid. Now, why does it only happen at the boundary? So a picture will help us illustrate this. So let's assume that our liquid is below this. Let's assume we're dealing with water, because water has famous examples of surface tension. Examples include that you can put water on top of a coin. You can try this at home. Use a water dropper. Drop it on the top of a coin, and you can see it bubble and bulge. You can actually fit quite a bit of water drops on the top of the coin because of the surface tension involved. So why does that work? Why is it only on the surface? Well, it has to do with how the atoms bind. If you have a water molecule down here, that water molecule can bind in a multitude of directions with other water molecules using its hydrogen bond. But the water molecule that's exactly on the surface has fewer places to go. Because of the way this binds, it actually creates a net downward force on the liquid. And so that downward force helps create that tension on the surface. Now, that force allows us to have the surface to have more resistance to being punctured and moved through. That's why some insects like spiders and water striders, things like that, can actually balance on the surface of a liquid because they are able to use that surface tension as the resistance force for them to hang around on the surface there. Water does this so well because it can form multiple hydrogen bonds. Now, surface tension also explains why sometimes it's hard to use water to do certain things. When we wash our hands with just water, a lot of times it doesn't get the dirt off. That's why we use something like soap. The reason for this is because to intermix and to pierce the water, you have to break through its surface tension. And so we use something called a surfactant. So these stand for surface active agents that break surface tension. Soap is a surfactant, and so it's used to break that surface tension to allow the water to bind to the things on our skin and mix with them, and thus make us cleaner. All right, let's move on to our last topic of discussion for today: cohesion and adhesion. So, one of the most common examples that you'll see with this is when we were working with test tubes or graduated cylinders. There was something called a meniscus in the test tube. So when you'd have a liquid in there, there'd be a kind of dip, and we called that the meniscus. And that has to do with cohesion and adhesion. So cohesion is kind of the attractive force to itself, attraction to self. So that would be, for instance, the cohesion of water would be the attraction of water molecules to other water molecules. Adhesion is the attraction to something else. So, for instance, that could be the water's attraction to the glass. So, in this liquid, the water has adhesion to the glass and cohesion with itself. And the fact that those two aren't balanced basically allows the water to cling to the glass to create a meniscus. So that is one example of cohesion and adhesion. Another one is capillary action. So capillary action is where liquids move along a material. If you remember back when we did paper chromatography, we put that piece of paper in a liquid and the liquid moved up the paper, and that's called capillary action. And the reason for this is that the water will adhere to the material, and then as it's a little bit higher, it'll adhere to the material above that, and so on and so forth. So let's briefly discuss how this is related to the kinetic molecular theory. So all particles move. Liquid particles, unlike gases, move, but they are attracted to each other enough that they stay close together. So this is how liquids differ from gases. Kinetic molecular theory says that all particles want to move. The gases move around wherever they want to go. The liquids move around, but they're also attracted to each other, so they try to stay close, and that's why they don't just fly around. This idea also helps us understand things like capillary action. Mild movement in particles creates this upward moving effect over time. All right, that covers liquids. Next time we'll get into solids. Hope to see you there.